Hi everyone, I'm Cheryl. In this problem, we're going to be identifying the extrema of my surface f of xy equals x squared plus y squared plus 2x minus 6y plus 6. We're going to do this in two ways. First, we're just going to observe by looking at what the surface is. And then secondly, we'll use calculus to back up that result. Okay, so let's begin by taking a look at what this surface really looks like. Well, what I'm going to do is I'm going to complete the square to help me get it into a standard form. So first thing, I will group my x terms together. So this will be x squared plus 2x, then y squared minus 6y plus 6. So notice I've grouped the x terms together and the y terms together. The next thing I'm going to do is add and subtract the same value to this side of the equation. So I'm going to have x squared plus 2x, and I'm going to add 1 and subtract 1. That way I haven't changed anything. Well, how did I know to add and subtract 1? I took the coefficient with the x, divided it by 2 and squared it. So 2 divided by 2 is 1, 1 squared is 1. So I added and subtracted 1. Now I'm going to do the same thing to the y grouping. So I've got y squared minus 6y. I'm going to take the minus 6 divided by 2, that's minus 3, and square it. That's 9. So I'll add 9 and subtract 9 so that nothing changes, and I still have that plus 6 on the end. Okay. What I'd like to do then is to group these three terms together because they factor into the perfect square, x plus 1 quantity squared. I'll also group these three terms together because that's also a perfect square, y minus 3 quantity squared. The remaining terms are all constants that can be added together. So negative 1 and negative 9, that's negative 10, plus 6 will give me minus 4. Okay. Now that I have it written in this particular form, I can see that my surface is going to be a paraboloid. Well, how did I see that? Well, what we can do is we can look at traces. So let's go ahead and look at traces, first of all, in the xy plane. So we're going to call these xy traces. So I'm going to consider some examples where z, the function value, is a variety of different numbers. So we'll start out with z being equal to 0. If z equals 0, my equation is going to be 0 equals the quantity x plus 1 squared plus the quantity y minus 3 squared minus 4. Adding 4 to both sides, I get 4 equals the quantity x plus 1 squared plus the quantity y minus 3 squared. And hopefully you recognize that this is a circle centered at negative 1, 3, with a radius of 2. So in my xy plane, I have a circle of radius 2. All right, well, instead of looking at the xy plane, let's move z up a little bit, and let's say z is going to equal 5. So let's see what happens when z equals 5. And these are just arbitrary numbers. I can let z be whatever I want. So 5 then is going to equal my quantity x plus 1 squared plus y minus 3 quantity squared minus 4. Adding 4 to both sides, I get 9 equals my quantity x plus 1 squared plus the quantity y minus 3 squared. And hopefully you recognize that this is also a circle centered at the same point, negative 1, 3. But this time, my radius is 3. I'm going to do one more. Let's try z equals negative 4. So this is going to be the plane below the xy plane. So I'm going to have negative 4 equals the quantity x plus 1 squared plus the quantity y minus 3 squared minus 4. When I add 4 to both sides, I get 0 equals x plus 1 quantity squared plus y minus 3 quantity squared. We can think of this as a degenerate circle. It's a circle centered at -1, 3, just like before, with radius 0. Really what I have here is just the single point, -1, 3. Okay? So this is really just going to be the point -1, 3. All right, so now for planes parallel to the xy plane, I have a pretty good idea of what this looks like. I'm going to start with a point, and I'm going to get another circle of radius 2, a circle of radius 3, and you can see as I go up, the radii of my circles are going to get larger. Now, to add a little more detail to this, let's take a look at traces in the other planes as well. So let's go ahead and take a look at the xz trace. And I'm not going to do three of them this time. Let's just take a look at what happens when y equals 0. So when y equals 0, my function looks like z equals the quantity x plus 1 squared, and when y is 0, this will be a 9 minus 4. Okay? So this is z equals the quantity x plus 1 squared plus 5. Hopefully you recognize that as a parabola. So in the xz plane, or parallel to the xz plane, I'm going to have a parabola. Okay, so this is a parabola. And let's finally look at the trace in the yz, parallel to the yz plane. So a yz trace. The yz trace, again, I can choose x to be anything I want, but let's just let x equal 0. If x equals 0, I'm going to have z equals, if x is 0, I'll have 1 squared, which is 1, plus the quantity y minus 3 squared minus 4. So this is going to be z equals the quantity y minus 3 squared minus 3. And again, I hope you recognize that that's a parabola. So now what I know is that in planes parallel to the xy axis, I'm going to have circles that continue to get larger. In planes that are parallel to the xz plane, I'm going to have parabolas. And parallel to the yz plane, I'm also going to have parabolas. This is going to create what's called a paraboloid. So very roughly, it's going to be something that looks like that. And our extrema value is going to happen, it's actually going to be an absolute or relative minimum, and it's going to happen at that turning point, which we've already calculated as being the point -1, 3. So I believe my relative extrema here is the point -1, 3. I'll be right back for part 2 to verify this information using calculus. In part 1, we discovered that our function was a paraboloid that had a relative minimum at the point -1, 3. Now we want to verify our results using calculus. So again, I believe my relative minimum occurred at the point -1, 3. Well, how do I use calculus to verify this? Well, I'm going to be looking at partial derivatives. So I want to find basically the critical numbers. So let's take a look at the first partial. So when I take the partial with respect to x, I'm going to be treating y as if it's a constant. So when I take the derivative, I'll have 2x plus 0 plus 2 plus 0 plus 0. Okay, so that's my first partial with respect to x. Let's do the same thing for y. So the partial with respect to y. This time as I go through, I'll be treating x as if it's a constant. So my derivative will be 0 plus 2y plus 0. Now I'll have a minus 6, and again, plus 0. All right, well, where do critical points occur? Critical points occur when either one of those partials is undefined or when they're both 0. Well, these partials are always going to be defined. So let's go ahead and see where they're simultaneously equal to 0. So I want to set 2x plus 2 equal to 0, and 2y minus 6 equal to 0. In this case, 2x equals minus 2, and x equals minus 1. And in the second case, 2y equals 6, so y equals 3. So now I know that I have a critical point at minus 1, 3. Now, just because it's a critical point does not mean it's a relative minimum, so I'm not done yet. I need to use the second partials test to see whether or not this critical point is a relative extrema or not. So we're going to use D equals the second partial xy plus the second partial of y, xy, minus the mixed partial squared. And in particular, we're looking to see what happens at my critical point, negative 1, 3. So I'll be looking at that second partial at negative 1, 3, plus my second partial of y at the point negative 1, 3, minus my mixed partial at the point negative 1, 3. So I'm going to need these second partials. So let's go back and figure out what they are. Because my first partial with respect to x is 2x plus 2, my second partial is going to be the derivative of this, treating y as a constant. Well, that derivative is just going to be 2. I need to do the same thing here for my second partial with respect to y. Again, treating x as if it's a constant, but that derivative is again going to be 2. The third piece that I need is the mixed partial. So what I need to do is I'm going to begin with my first partial with respect to x, so that's this equation, and I'm going to take the derivative with respect to y, which means I'm treating x as a constant. And if x is treated as a constant, this is going to equal 0. All right, so let's fill it in to my second partial test. The second partial at the point negative 1, 3. Well, you know what? It's 2 all the time, no matter what that value is. So this is going to be 2. My second partial at y at the point negative 1, 3 is also always 2, so I'll add 2. My mixed partial is going to be 0, and so that should be 0, that should be squared here. So I have 0 squared, which means that my d value is a 4. Because this number is positive, that guarantees that I have a relative extrema at the point negative 1, 3. So I know now that it's in a relative extrema. But what I don't know is it a relative minimum or a relative maximum? To make that determination, let's go ahead and take a look at the second partial with respect to x. And in particular, I want to look at what's happening at the point 1, negative 3. Well, I've already done this calculation. I know that the answer is 2. Okay? Because 2 is a positive number, remember second partials, you're thinking in terms of concavity. So if it's positive, we're thinking concave up. If it's concave up, and I know it's a relative extrema, it must be a relative minimum. So we do know now that there is a relative minimum at the point negative 1, 3. I hope that was helpful. Thanks.